Alright, so last time we talked about projectile motion where our projectiles were launched at in the horizontal direction. So they were launched like this and they would fall to the ground, and we determined some things about that kind of motion. This time we're going to discuss a different kind of projectile motion, that is where our projectile is launched, let's say, from the ground level at an angle, and it's going to sail through the air and it's going to return to the ground at the same height. And so one important feature that we're going to note about this kind of projectile motion is that we do begin and end at the same height. We're not, for instance, firing from one height, a cannonball perhaps, and it landing at a different height. This is firing from the ground and the object returns to the ground, much like a football or a golf ball would. So once again, here's our ground, and what we're going to do is we're going to take our projectile, and this is the place from where we're going to launch it, and it's going to follow the trajectory, and we'll notice that the trajectory for projectile is a perfect parabola. So I'm trying my best to draw a perfect parabola, and we're going to put a few points of interest here on our image so we can kind of visualize this kind of motion. You'll notice I'm putting some of these objects at key locations, and now you'll notice that these vectors are at key these projectiles are at key locations. This is the same projectile moving through this entire path. Let's say this is where it is at time equals 0, and then after 1 second it's at this location, and after 2 seconds it's at this location. And notice that the height that it traveled during the first second is greater than the height it traveled during the second second, which is greater in turn than the height it travels during the third second. And then after that, during the next full second, it drops back down to that same height, and then after the next second back down to the height it was after the first second, and then here at the end it returns to the same height. So we see there's this perfect symmetry in the motion. Right here at the very maximum height, at the max height, it is exactly halfway across its range, where if this was a measurement we called x, the range, exactly halfway would be underneath the max height. And this would be at exactly half the time it took for the projectile to do this entire trip. So there's some symmetry that we'll see here, and we can use that to our advantage. And notice that if we just look at motion in the y direction, that the object is slowing down. It's moving quickly in the upward direction at first, and then more slowly, and then it stops. We see that because this is the same type of motion we'd see if we threw this ball straight up. It would slow, come to stop, and then return to the ground and speed up on its way. So we see that same type of motion in the y direction. Meanwhile, the object's moving in the x direction at a constant velocity. So let's pick up some of our vector arrows to show that kind of motion. So we're going to put this x vector, this vector that shows the velocity in the x direction. You're going to notice that it's the same arrow I'm using throughout the entire image, because in the x direction, I missed one, this object is traveling at the same velocity the entire time in the x direction. That never changes. However, in the y direction, we'll see that this object begins at perhaps a much faster velocity, and I'll do my best to show that by changing the lengths of these arrows. So this one will be the fastest in the upward direction, in the y direction, and then this next vector would be somewhat smaller because we're going to show that it's not quite as fast in the y direction. And then by the time we get to this vector, it's barely moving. So maybe I should bring some of these vectors down just to show the relative scale. So if I can catch this, there we are. So there we go. We see that the vector at this point is much larger than here, and this is much larger than this one, and this one has no y component whatsoever. And then what happens as the object begins to fall is that we see that the vectors are going to begin to point downward, and here it has a very small velocity in the downward direction, and in this vector we see that the velocity has increased, and yet increased again when, bring it all the way down like this, when it's just about to hit the ground. Alright, so there are two principles that we want to remember here. One is that there is an independence of motion. That is, as this ball flies through the air, its motion in the y direction, where it's slowing down on the way up and speeding up on the way down, is in no way related to its velocity in the x direction, which, as you can see by the length and shape of each of these vectors, is the same throughout the motion. The other important principle here is that if about an imaginary line right here, there is perfect symmetry. That is, the time it takes for the projectile to make it up to the top, which we call the max height, is exactly the same as the time it takes for that projectile to land. And we can use that to our advantage. After all, if we know what conditions are necessary to get the projectile up to this point, then we know exactly what's going to happen on its way back down. If it took 1 second to go from its origin to here, it'll take 1 second to go from here down to the ground. If this is 1 second before the max height, then this is 1 second after the max height. So from this point forward, it begins to look like a horizontally projected projectile problem, rather than a projectile launched at an angle. What that also implies is that the final velocity here when it strikes the ground is identical in every way to the initial velocity here, both in terms of x velocity, which we can see is the same, y velocity in terms of magnitude, but of course the direction is now pointing down, and even the angle of the initial vector. If this was, let's say, 60 degrees above the horizon, then it will land at 60 degrees below the horizon. So there's this perfect symmetry, and we can use that thinking to our advantage. Now, our problem-solving strategy when we were presented with a projectile moving at an angle, launched from the ground and returning to the ground at the same height, is as follows. We want to first find out the amount of time that the projectile is going to be in the air. The total time it's going to be in the air is what we call hang time. But also significant is the time it takes for the projectile to get to this location at the very peak, at its max height. Because between the amount of time it takes to get up here is exactly the amount of time it takes to come back down. Secondly, we want to find how high this is. What is the max height? So from this point to this point, what is the height or the altitude of our projectile? Next, we want to be able to find the range. That is, how far downrange our projectile landed. And that is, it's moving at a constant x velocity for this entire hang time, which will bring it this far downrange. And then lastly, we want to find, if we don't already know it, the final velocity. What is the magnitude and the direction of the projectile when it hits the ground? So let's make some room and figure out how we're going to solve a problem that looks like this. And we'll put it up there so you can still see it. And alright, so there are two different ways we can go about finding the amount of time that a projectile is in the air, the hang time. And we'll start by calculating the time to the peak, and we'll use the idea of this symmetry to our advantage. So what we're going to do is we'll assume that we have a projectile, and it's going to be launched at some angle, theta, off the horizontal, and it's going to fly through the air and it's going to land over here. And it's this point right here at the very max height that we're interested in. So we're going to call that height y. Now, the easiest way to go about finding the time is if this height y is given, if you know this value, then what you could do is say that, alright, I know that any initial displacement plus any initial velocity times time plus 1/2 gt squared is going to be true for this situation where this is the height y right here and there is no initial displacement, and we can assume that instead of launching something from here and it ending up here, that rather we drop it from rest here and it lands down here, because it's the same type of motion. So if our initial velocity in the y direction is 0, then we can get rid of that, and we have y equals 1/2 gt t squared, and so to solve for the time, this would be the half time to the peak. It would be square root of 2y over g. But let's suppose that we do not have the max height, and that's not given. Well, how can we go about finding this solution? Well, we know that this initial velocity vector has both a velocity component in the x direction, and it also has a velocity component in the y direction, and that would be its initial velocity in the y direction. And we know that its final velocity in the y direction at the very peak, at the very max height, is 0 meters per second. So knowing that, we can say that time is equal to the change in velocity, that's our VF minus our VI, over the acceleration due to gravity. And since VF is 0, we'll have time equals our initial velocity, which could possibly be negative, if upwards is the negative, or rather if down is the negative direction, that would be 0 minus this positive number over g, which would be negative 9.8 meters per second, and that would give us a positive time. You know, if you get negative time, you did something wrong, and that would give us the time to the peak. So either of those two ways will be sufficient for finding the time it takes to get to the peak. And then what do you do with that time? If you have the time it takes to go from here to here, and that's the half time, well, then you simply multiply it by 2, and that'll give you the entire hang time as it goes through the entire parabolic trajectory. So that's how you're going to find the time. Now, once you know time, you want to find the max height, and the max height is going to be this y measurement here, and if it's not already given, we've already established that y is going to be equal to 1/2 g times t squared, and we already showed you how to find the time. So you plug in the time, and that would be not the whole hang time, but the time to the peak, multiplied by 1/2 g, that's 1/2 times 9.8, which gives you 4.9, and that would give you the time, or rather the height at its maximum peak. Alright, now to find the range, which is what we're going to call x, we know that because we've already established that there is this independence of motion, that what's going on in the x direction is independent of what's going on in the y direction, except that they're both connected by time. And if we figure out what the velocity in just the x direction is, and the total time it takes to go all the way up and all the way back down, that's the hang time, we can say that the distance is equal to velocity in the x direction times that amount of time. And that will give you the full range of the projectile. Alright, and then lastly, we want to find the final velocity. Now, if the initial velocity is already known, we know that the final velocity is going to have the same magnitude, and the angle will be the same, except it will be below the x-axis rather than above. But if we don't know the initial velocity at launch, then we can say we have this is our projectile just at the instant that it's going to land on the ground, just the instant before. We know that this projectile has both velocity in the x direction, which it's had for its entire trip, and it has the velocity in the y direction, which we could say is Vf in the y direction, which equals Vi at the top of the peak, which we said was 0, plus g times t, where t is the half time, that is the time it takes to go from this location, let me show you that a little bit better, from this location here down to here. It's accelerated in the y direction to gain this final velocity. So that will give us the final velocity in the y direction, and you'll notice then that we have this right triangle whose one leg is the x velocity, which has remained constant, the other leg is the velocity at the end of this free fall from its max height, and the resultant, this vector here, will be its velocity in the end, and you can get that using the Pythagorean theorem. We could say a squared, and we'll call this a, and if this is b and this is c, we'll say a squared plus b squared equals c squared, and you take the square root of that. And then of course you want to find this angle theta right here, if that's theta, and we know that this is the opposite side of that angle, and this is the adjacent side to that angle, then we can just say that theta equals the inverse tan of our opposite, which is our final velocity in the y direction, over our adjacent, which is our velocity in the x direction, and that will give us this angle here, theta, for our final velocity vector. Well, I hope this was helpful.